Hi! Today, I am going to present a paper, Server-Driven Video Streaming for Deep Learning Inference. I am Kuntai Du, a first-year PhD student from University of Chicago. This is a joint work with Google Brain. After this 10 minutes talk, you will be able to learn about a new server-driven approach in video streaming for analytics scenario. So now, let's start. Nowadays, video streaming for deep neural net-based analytics is more and more pervasive. For example, people use wildlife camera for the animals. On the street, people deploy traffic camera to monitor the traffic. People also use drone camera to efficiently collect information in a wide area. As so many video streams are waiting for analytics to generate valuable insights, our goal is to scale out video streaming for analytics. To achieve this goal, we need to design a video streaming protocol that streams the video from the camera through the network and to the server-side deep neural net, DNN for short. To make video streaming protocol scalable, we focus on two critical design goals. First and foremost, in order to make the analytic results valuable, a video streaming protocol must preserve high inference accuracy as if the video is sent into the server-side DNN in its entirety. Second, a video streaming protocol should also save bandwidth. This is because the bandwidth cost of, for example, the cellular network will be proportional to the total data sent. By saving the bandwidth, we can save more and more bandwidth cost as the video streaming time grows. On the other hand, the streaming delay per frame is proportional to bandwidth usage per frame. Hence, saving bandwidth will reduce the streaming delay per frame and thus reduce the overall delay. But where is the research opportunity for us to meet these two design goals? Luckily, video streaming for analytics as a new type of streaming opens new research opportunity in terms of bandwidth saving. Traditionally, the video is streamed from the video server to the human viewers who care about the global visual quality. As shown on the left side, since every pixel contributed to the overall visual quality, the video streaming codec has to stream all pixels with nearly the same quality, including those pixels that are not relevant to the inference results, like the street and the tree. But in our scenario, the video is streamed from the camera to the server-side DNN, which only cares about the inference accuracy. So we can aggressively compress those pixels that are not related to the inference accuracy. In the right figure, we mark those pixels that can be aggressively compressed as gray. In short, video analytics enable aggressive compression of non-object pixels, like tree pixels and street pixels. However, we are not the first one who see this bandwidth saving opportunity. So now, let's see how previous works explore this opportunity. One common approach is real-time camera-side heuristics. These approaches use real-time camera-side heuristics as a filter to draw pixels that are possibly irrelevant to the final analytic results. Concretely, the camera first captures the frame, and the camera runs camera-side heuristics in real time to filter out some pixels that are irrelevant to the inference accuracy. The camera then sends the remaining part to the server. After that, the server performs DNN inference and obtains the analytic results. But real-time camera-side heuristics are bound to be suboptimal. For example, let's compare the frame sent by real-time camera-side heuristics and the ideal frame that includes all object-related pixels. We see that camera-side heuristics may miss many objects, like the 4 objects on the top right corner and the 2 objects on the bottom left corner. This is because camera-side compute is too limited to support accurate heuristics. Based on this observation, we argue that in order to be accurate, we must put the real-time heuristics on the server instead of on the camera. It seems simple to meet this requirement on the first look, but after we dive in deeper, surprisingly, we find that there is a critical chicken-egg problem lying behind and make the whole thing difficult. To let the server-side DNN model drive the pipeline in real time, the camera needs to use the feedback from server-side DNN on current video to encode the current video? How can we use the egg feedback to edit the chicken video? Our solution is to let the server see the video first and then iterate on how to encode the video. To instantiate this concept, we present DNN-driven streaming, DDS for short. Specifically, the camera first buffers several frames to form a video segment. Then, the camera encodes this video segment in low quality and sends it to the server. Upon receival, the server feeds this video segment to the server-side DNN and gets the inference results and the feedback regions. Here comes the key of DDS. Different from previous works, DDS chooses to perform an iteration by re-encode the server-side DNN feedback regions in higher quality. Concretely, the server sends the feedback regions back to the camera. The camera then re-encodes feedback regions in higher quality and sends the video back to the server. Last, the server feeds the resulting video to the server-side DNN and updates the inference results. With this illustration in mind, let's take a look at a demo. Here, we use blue bounding box to mark the objects detected before the iteration, and use orange bounding box to mark those objects detected after the iteration. The first video shows the detection results before the iteration. The second video shows the video the DDS sent for the iteration. The third video shows the detection results after the iteration. So now, let's watch some videos. From these videos, we can see that when the first video misses objects, DDS will try to encode them in the second video, and ultimately recall them in the third video. From this demo, we can get a sense that DDS encodes and recalls undetected objects through the iteration. Why DDS can recall the undetected objects? The secret lies in the way we generate the video sent for the iteration. To illustrate our method, we take object detection as an example application. First, from the inference process, DDS gets all regions that may contain objects, as shown in the blue bounding boxes in the figure. These bounding boxes are generated from intermediate output of DNN, so there is little overhead. Second, we eliminate those regions that are already confidently detected by the DNN. So in the figure, 3 orange bounding boxes are eliminated since DNN are already confident about them. Third, we encode these regions in a higher quality. In short, DDS finds the regions that are almost detected but not. This "but not" is a key differentiator between previous works and DDS. Previous works pursue a complete coverage of objects, but DDS covers a subset of objects that are not detected. After introducing the technical details of DDS, let's take a look at experimental results. We demonstrate that DDS is able to hit a better bandwidth accuracy trade-off. In this figure, the x-axis is a normalized bandwidth consumption, the y-axis is the accuracy. So the top left direction is the better direction. These ellipses shows the standard deviation of DDS and the baselines. From these ellipses, we can see that DDS outperforms the baselines. Quantitatively, DDS can save up to 59% bandwidth as well as achieve higher accuracy. To wrap up, our contribution is that as for bandwidth accuracy trade-off, we need to use a real-time server-driven approach. To implement this concept, we present DDS, which uses an iterative workflow that lets the server see the video first and then iterate on how the video should be encoded. Experimental results demonstrate that DDS is able to hit better bandwidth accuracy trade-off. Please check my personal webpage for DDS-related resources and lessons that I learned from DDS. That's all. Thank you.
Thank you, Quinten. So let's take some questions. The first question Slack is from Hyunho Hyo. The question is that it's trying to contrast this design by saying, how might the solution change if you can actually run a small neural network at the camera? Cameras often are fixed. And so, there is sufficient amount of temporal redundancy, which means that this lightweight model, even if it's not very accurate to start with, can be fine-tuned over time to run on the camera itself. Given that design space, how does DDS figure in?
Okay, so my intuition is that it kind of really depends on the video content. So if the video content is like relatively simple and has strong temporal correlation and redundancy, then it is a good choice to try to use some cheap specialized DNN on the camera side because it will be pretty accurate and can efficiently filter out many frames. But if the content is really complicated, like in a drone camera, assume that a drone camera like flying in the city and goes from this street to that street, then the content will change very fast and there is little redundancy there. So in that case, we might want to like not trust the compute power on the camera side because it do not have sufficient compute to actually explore that complex scene. So in this case, it might be better for us to just stick to the server-side compute and run server-side models there. Yeah.
Cool. In fact, I had a follow-up myself to your answer is if, it makes sense that it's a more dynamic camera setting that makes, there's more applicability on the server-assisted streaming. But in a more dynamic setting where the camera itself is moving around like a drone or something, isn't there an alternate open question about the connectivity between the camera and the server itself now that is much more unreliable compared to a static camera? As the drone moves around, the connectivity to the server itself might not always be available, right?
Yeah, we completely agree to that point. So that's why we somehow raise the streaming bandwidth because streaming bandwidth, it will somehow like suffers, the video stream will somehow like survive under very low bandwidth. Yeah.
Okay. The next question is from Slack, which is that what happens if the DNN entrance at the server actually cannot detect the regions and the bounding boxes because of just low quality video in the first iteration itself? There can be a drop in recall more specifically because it's not even detected, which means in the further iterations, there's no chance for it to be encoded in a better quality at all. How do you deal with that drop in recall?
Let me think. That's actually a pretty good question. It somehow illustrates like one potential limitation of DDS. So in our experiment, we find that in the first iteration, the video quality can't be too low if the video quality is way too low, then it cannot provide reasonable feedback. It will miss all those small objects and result in poor accuracy. But if the video is like have mediocre quality, then it is able to actually detect. Surprisingly, it can actually get tons of objects there. It will actually nearly cover all objects. And in that case, DDS can work pretty well. Yeah, hope that answered your question.
Okay, sure. And let's take another question, which is that what is the conceptual difference between what you've done with DDS and just the big region, the big body of work that exists in region of interest based encoding?
The main difference is that DDS tries to propose regions outside the video source, and region of interest methods, they propose regions, they have the raw video in their hand. So in DDS, there is some extra communication overhead between the video source provider and the region proposal, like the region proposal algorithm. Yeah, so in DDS, we have to overcome that limitation through one extra iteration. Yeah, I think that also illustrates the main difficulty of DDS.
Cool. I think there are a few more actually questions on both Zoom and Slack, but I guess in the interest of time, we could move on. Thank you, Kuntai, but please go ahead and feel free to engage with these with the questions on both these channels.
Yeah, thank you, Dinesh.
Thank you, Kuntai. So let's start off with a question from the Zoom Q&A. So Jae-Hong asked, your system seems to require extra encoding and inference on the second iteration. How much additional overhead does the system impose to both server and the sender side?
Okay, so basically DDS only requires the encoding capability on the camera. So at the camera side, there's little overhead. And at the server side, DDS, like it typically requires 2 times of inference on each frame. So if we compare to the very initial approach that we just do inference on 1 frame, that is 2x overhead. But however, first DDS is able to save bandwidth. Saving bandwidth itself is you can also save a huge cost. For example, if your video is streamed through the cellular network, like maybe 5G plan, then if you can save half of the bandwidth, you can save half of the cost. And also, other approaches that leverage server-side compute. There's other approaches that also tries to leverage server-side compute to do some like very clever thing, and typically they have more overhead than DDS. For example, one previous work like AW Stream, it will take approximately 3 to 4x overhead on the server side. So though DDS is like it somehow takes more compute on the server side, it can still hit a desirable cost if the bandwidth cost is relatively expensive and the server side cost is relatively cheap.
Great. So I think I can combine Harry's question and Taku's question. So there are a lot of questions on the latency induced, and Takuya says that I think data storage on the camera side is required to store the captured data until the server provides feedback. Have you evaluated how much data storage is required on the camera?
Okay, so let me answer them one by one. So could you please repeat that question? I somehow forgot the first question.
So there's a latency issue, right?
Mm-hmm.
Because you do second iteration,
Mm-hmm.
and also you need to store some of the data, the recent video on the camera side, yeah, until the feedback arrives. So have you evaluated these overheads?
Okay, so first for the latency issue, the worst time latency is, it is actually higher because DDS first need to buffer some frames at the camera side to form a video segment. It itself is a buffering time cost. And also DDS have to run an extra iteration to further improve the accuracy. So if we consider worst time delay as a metric, DDS will be suboptimal. But we actually find that DDS can generate about 90% of the results before the iteration. And this part of results are delivered from low quality video. So the streaming delay of this part is actually shorter. And so actually in average, the average response to delay per inference results is actually pretty low. Yeah, and as for the storage, we evaluated that on our implementation, and it typically requires, let me see, 2 to 3 seconds of storage. So storage in 2 to 3 seconds video is, it is pretty low overhead, and you can even put all the things in memory and just load it while we use it. Yeah, thank you.
Great. Another question. Can DDS handle quickly changing videos?
Yes, DDS can handle quickly changing video. The rationale is that DDS do not rely on DDS just iterate on the current frame. So for each frame, DDS will look it twice. And also DDS does not try to do something like learn from previous video and use the experience on the future video. So without this generalization, without this kind of adaptation, DDS is actually able to, DDS is able to decouple itself from but DDS is able to just merely look at current frame instead of learn from previous frame that may lead to a wrong results. I think that basically is how DDS handles the how DDS handles the content change. Yeah.
I see. So I think I have time for one more question, and I'll use that to my advantage. I have one question. So I've seen a lot of papers that in video analytics that use multiple cameras. So these they target problem domain where there are multiple cameras. So can you extend DDS to work with multiple cameras? And is there anything that you have thought of to save more bandwidth there?
Okay, so for multiple camera, at least from my perspective, the main research opportunity lies in how to deal with inter-camera redundancy. And yeah, so exploring this opportunity is somehow like it will somehow like related to tasks like ReID identification and some tasks like tracking, or like how do you translate one object in one camera to the other camera. So at least from this perspective, I think they are somehow operating on a vertical plane, on a like another design dimension compared to DDS. So so I think there is some like very general approach that can translate like from the bounding box of one camera to another camera. If that approach exists, DDS can naturally benefit from it. Yeah, that's my answer.
Right. I imagine if multiple cameras send the low resolution version, most of the objects have been detected, right? So you see much less how do you put it, detected almost but not, right? So those percentage will decrease.
Yeah, that's true.